Descriptive Statistics, Part 2. Up until this point, we have been a bit sloppy in not distinguishing between population values and sample statistics. Population values are truths. They do not have any uncertainty associated with them. If you take up all the values in a population and find the mean won't change tomorrow if you do the same thing. However, you can grab several samples from the same population, and each time you may get a slightly different mean. Therefore, we will distinguish population values as population parameters and denote them with Greek letters: mu for the mean, sigma squared for the variance, and sigma for the standard deviation. The mean is defined as it was before. Nothing is different here. We sum up all the values and divide by the total number of observations. The measure of the variance is a little different. We are still looking for the average squared deviation, except this time we are dividing by big N and not n-1 as we do for samples. There are corresponding population parameters to go with our sample statistics. We use our sample statistics to help us learn the population parameters. Mu for the sample mean, sigma squared for S squared or the sample variance, sigma for S or the sample standard deviation, and big N for population size and little n for sample size. For symmetric distributions, there is one statistical phenomenon that is important. It is called the empirical rule. Think back to the z-score, which tells us distance from the mean. The empirical rule states that 68% of the data are found within one standard deviation of the mean. This is the blue shaded area. Within 2 standard deviations from the mean, we have 95% of the data. This is the green shaded area. And within 3 standard deviations from the mean, we have 99.7% of the data. This is the orange shaded area. Remember, our rule for outliers is if the z-score is greater than 3, we say it's an outlier. The reason is it's useful because according to the empirical rule, only 0.3% of data lies beyond 3 standard deviations, so outliers should be viewed with some suspicion. For population of math SAT scores where the distribution is bell-shaped, the mean is 500 and the standard deviation is 90. Then we can assume that 68% of test takers score between 410 and 590. 95% of test takers score between 320 and 680. And 99.7% of test takers score between 230 and 770. Okay, but what about for non-symmetric distributions? Then what? In this case, we use Chebyshev's rule. Regardless of how the data are distributed, at least 1 minus 1 over k squared times 100% of the values will fall within k standard deviations. So here k is the number of standard deviations we're considering. The standard deviation of the mean for k greater than 1. If k is equal to 2, i.e. 2 standard deviations away from the mean, then 75% of the data are covered. 3 will make 89% of the data. Another visual tool we can use to indicate the distribution type is a quantile measure. Think of separating the data up into 4 blocks. The first quartile tells us where 25% of the data are smaller and 75% are larger. The second quartile is just the median, so it's 50-50. And the third quartile tells us 75% are less than this value and only 25% are greater than this value. To determine a quartile, you need to find its position in the ranked data when n is the number of observations. The first quartile is going to be 25% times n plus 1. The second quartile is going to be 50% times n plus 1. And the third quartile is going to be 75% plus n plus 1. The formula is always going to be percent times n plus 1. Let p be the percentile you're interested in as an integer. E.g., p is equal to 25 if you want 25%. Let n be the sample size. To find the position of the number you can multiply p divided by 100 times n. So for example, let n equal 12 and p equal 25, then p divided by 100 times n is equal to 3. Another example, let n equal 10 and p is equal to 25, then p times n is going to be 2.5. If the value of the position is an integer or whole number, then use the value as the correct position. If the value is not an integer, then you round up to the next integer. Or you can use the n+1 rule and round down. Here's one example. We have 9 observations. So we want to find the 25th quartile. So we're going to do 25% times 10, which is going to be 2.5. In which case we're going to round up to 3. In the third position is the number 13. We do the same thing for the third quartile. So we're going to multiply by 75% times 9, and we're going to get 6.5, sorry. So we're going to round up to 7, and in the 7th position is the number 18. The interquartile range, also called the mid-spread, is a measure of variability. Measures the spread in the middle. 50% of the data is the range of the inner 2 quartiles, that is Q3 minus Q1, and it's not influenced by outliers or extreme values. We can graph the quartile values using a box plot. Notice it contains the full range of data as well as the interquartile range and the median. So here is the full range. Remember, that's x max minus x min. And here's the interquartile range. And here is our median. We can use these 5 numbers to again indicate skewness. You can see that the data are left skewed when we have the majority of the interquartile range to the right of the range. It's symmetric when the interquartile range is in the center of the range, and it is skewed right when the interquartile range is to the left. The way to think about that in terms of a graph here is that the peak is occurring either further to the right at the center or further to the left. Notice when we talk about skews, we're talking about the long part of the tail. So that's why this is skewed to the left and this one is skewed to the right. Here's one example. The range is 27, but the interquartile range is only 3. Here's our far outlier. We can also use Excel to construct a box plot. First thing you need to do is sort the data. Then we need to find the position of each quartile using the percent multiplied by the sample size formula. So here are our data. We sorted it out. And now what we're going to do is we're going to calculate the percentile. So we have the number of observations, the percentile we're interested in, and we're going to do percent divided by 100 times our number of observations. In this case, it's going to be 63. So we're going to go down to position 63. Finally, we round up when we get non-integer results. So when we have 52.50, as we do for the 75th percentile, we have to round up to 53.